So here are a couple of slides showing the post-gate renormalization method and seek method. This page shows the post-gate renormalization method. This figure shows the edge renormalization function. Consider processing a rectangular function. It will show the edge effects after gating. The gated raw data will be divided by this renormalization function. So this method is used by KSAT, Rode-Schwartz, and Copper Mountain. The post-gate renormalization method makes two important assumptions. First, the edge effect from the rectangular function is similar to that from the raw data. Second, it assumes the time domain path is centered around the gate. Violating either condition will result in enlarged edge arrows. This figure shows two different time gates. The red curve is a gate which is centered around the time impasse. The green curve is another gate which is not centered around time impasse. In this figure, we can see the red curves have much less edge effects compared to the green curve at the two edges of the frequency band. The seek method is called spectrum extension edgeless gating. In this figure, the raw data is the black line, and the blue line is the gate kernel. So this is in frequency domain. So gating is a sliding convolution in frequency domain. The edge effect comes from the discontinuities at the edges. So the edge effect is caused by half data missing for convolution at the edge. The seek method extends the spectrum data beyond the edges so the data does not drop off a cliff. The seek method is patented. The author is Zhang Chen, the chief engineer of ETS-Lindgren. Autoregressive method is used to extrapolate data in frequency domain. There are a couple of benefits. It is robust and fast, can be done on the fly. An AR predict data is a linear sum of the known data. The new data is therefore linear combinations of real physical data. If we use seek, the post-gate renormalization is not needed. This figure shows the comparison of seek and renormalization method for real measurement data. It shows comparing to the reference data, which is the blue line, the seek data, which is the green line, has much less edge effects compared to the light blue line, which is the renormalization method. This page is a summary of the seek method. The seek method can reduce edge arrows even for data with large slopes near band edges. The figure 1 is the data with large slopes. Second, it is not burdened by gate centering. As we mentioned, if the gate is not centered around the time impasse, the post-gate renormalization will have large edge effects. But seek is not burdened by gate centering. The SIG method can also work with complicated gates, such as multiple band. It can also accommodate null gates without severe edge errors. Let's still use this data set to show the post-gate, the renormalization method and SIG method. So this is the app written in C#. We are still using this data set, which is a pair of 3181 mini biconical antennas. The mean time impulse pulse happens at 6.12 nanosecond. So now our time gate is centered around the mean time impulse. Let's zoom into the edge of the frequency domain. Okay. Now the gate is centered around time impulse, and we use the renormalization method. The gated curve doesn't have a lot of edge effects. But if we change the gate starting time to, for example, 2.12, now the time gate is not centered at the mean time impulse. We can see there are big edge arrows on the frequency domain gated data, which is a red curve. Let's choose SIG method right now. Apply. So here, we can see if we use SIG method, even the time gate is not centered at the time impulse. The gated curve in the frequency domain doesn't have much edge arrows compared to the conventional renorm method.